that we know how to find the derivative, we're going to use that skill, the ability to find that derivative and the ability that we can find it pretty quickly now. We're going to use that to find some critical points on some graphs. And by critical points, that means the max and the min and what we call the point of inflection. Now in class, we started with a review, and there's a 3.6 practice worksheet. It's a copy of a worksheet. We did that in class to kind of help review some skills that could probably hurry you up on this. So if you wanted to go look through that, you can do that. You can pause the video, come back. If not, I'm going to keep on going. What we want to do is first look at a curve and put that tangent line on that curve and look at when, and kind of comparing the slope of that tangent line and paying attention to when it's positive and negative and zero. So in this example, you can see my purple dotted line. That's my tangent line. And right now, it is headed upward. So that has a positive slope. If I take that, and I'm supposed to be able to move this. Let's see how this works. Okay, I probably have to sorry. All right, so I'm going to grab that tangent line and I'm going to slide it over that curve. And I want to pay attention to when that tangent is positive slope and when that tangent has a negative slope. So you can see right here, all the way along here, it has a positive slope. Down here, see how my curve gets pointy? That's one of those exceptions where the tangent doesn't exist, and then it goes back up like this. Okay, so now you can see my line is headed downward, so that has a negative slope. What we're trying to do is pay attention to what's happening with your curve as that tangent line changes from positive to negative slope. And also what happens right here. Notice right there, I create a horizontal line. And what's the slope of a horizontal line? Well, that's 0. So it was positive, it's 0, now it's going back and it's negative. Let's come on down here. It starts to curve back, and then I'm back down to this. And so hopefully what you can tell from this is that anytime your curve is on the downhill slide, so it is decreasing, then the slope of your tangent line is going to end up being decreasing, and it's going to be negative. But if your curve is on its way up, like it is right here, if your curve is increasing, then your slope will be positive. All right, so let's use that. You're going to need your worksheet from last night, your homework where we did that 15 through 38. We're going to take it to the next step. We're going to look at number 39 on that worksheet. If you need to pause the video and go grab that, do that now. But what it said here is that number 39 gave you this function, y equals x squared plus 2x. And it said to use a graphing calculator to graph the derivative of each function. So the first thing you would have to do is find the derivative of this function. The derivative, it's a quick, easy one, 2x plus 2. And then what I have here is I have already graphed a y equals 2x plus 2. You can see here's my y-intercept of 2, slope is 2. So I've graphed the derivative. And it says use the trace function to find the values of x for which the slope of the tangent line, y, is positive, negative, and 0. All right, so if I have this graphed, I'm basically just looking, when are my y values positive, negative, and 0? Well, y is positive anytime I'm above the x-axis, so all of this would have a positive y value. All of this would have a negative y value, and right here, the y value would be 0. So I'm going to say that the derivative is positive, and remember it said to write the x values. So the x values, when the derivative is positive, would start right here at x equals -1, and then would go on forever. So it's positive from -1 to infinity. the derivative is negative, well, if you go back to your graph, that's when my y values are negative, but I'm supposed to list the x values when that happens. So the x values would be anything smaller than negative 1. So negative infinity to negative 1. And the last part says find out when the derivative is equal to 0, and that happens right here when x is negative 1. So they're having you look at the derivative graph to figure that out. I think it makes more sense if you look at the original function and pay attention to that. Remember we said that anytime the function is increasing, so that would happen on all of this part of the parabola right here. This is the original function. This is this graph right here. So all of this is increasing. So your tangent line, if you were to draw it this way, right here, these are bad tangent lines, sorry, but any of these tangent lines right here, all of those would have a positive slope. Way up here, it would have a positive slope. Anywhere on the right side of that parabola because the function is increasing. Now notice that that function is increasing starting right down here at this minimum, and notice what that value is, that x value. Well, that's negative 1. That's that negative 1 we were using over here. That's that special point. That vertex right there is the cutoff from the function increasing versus the function decreasing. So anything on the right side of that would have a positive slope. So this should make sense right here. Anything on the left of it, I'm probably, so if I were to come over here, all of these tangents, these all are decreasing, so they have a negative slope, and they're all the ones that are from negative infinity to negative 1. Now that's all fine and dandy. So this kind of helps us know when the function is increasing and decreasing, but this is the spot we really care about. This is your minimum. That's one of those critical points we were talking about. Remember that at that spot, the derivative or the slope of the tangent line, well, your tangent line would look like this, and it would be a horizontal line at that spot. And so the derivative at the minimum there is actually going to always be 0. If it was a parabola that opened downward, your tangent line would be right here, and it would be horizontal, so its slope would be 0 right here at the maximum of your parabola. So that's kind of a handy feature. But for right now, I got ahead of myself. Right now, they just want you to graph this tangent line, figure out when it's positive, when it's negative, and when it's 0. Now, I did number 39 with you. You need to do 40 and 41 for your homework. If you want to pause the video and go do it right now, that might be smart. So let's look at that special situation. This is consider what is happening on the graph when the slope is equal to 0. So I already kind of told you that that's going to happen if you're at a maximum right here at this vertex. The slope would be 0, or if you're at a minimum, the slope would be 0. And it doesn't have to be a parabola. It could be any kind of a polynomial function or any function that has a maximum, and as that tangent line rides across there, it would hit right there, and it'd have a slope of 0. It'd hit right here, it'd have a slope of 0. Here, here. So all the places where you have mins and maxes, your slope of your tangent line is going to be 0. What's handy about that is maybe now, remember how we always would find the max and min in our calculator? We'd have to go to that second calc and do max and min. Now we have another way to do that, and probably a quicker way, where you can just find your derivative and use that to find where your max and min happen. And we wouldn't even have to really even be looking at a graph to figure that out. Let's try one. All right, here's an example where I've given you a cubic function. I'm going to find the derivative to help me find the max and the min. The derivative of this function would end up being a 3x squared minus 10x minus 8. Now what I'm going to do is find or solve this well, let me backtrack. Remember that this is the slope of the tangent line. The derivative is the slope of the tangent line. And I'm looking at when the slope of the tangent line ends up equaling 0, because I know it'll be a horizontal line. I'm going to put 0 in for the derivative and solve it for x. That will end up giving me the x value when the slope is 0. Let's factor this. Factors of 8, I'm going to go 4 and 2. It could be a negative 12, positive 2. Set those each equal to 0. X will end up being negative 2/3 and 4. These are the x values where that slope will equal 0. So those are the x values of my mins or maxes. To find the actual coordinates, I would have to plug those back into the original function. I would take the negative 2/3, I'd go plug it back into all the x's up here, and find the matching y value. And then I would do the same thing with my 4. Go plug it in for all of the x's. Get the matching y. So I'm going to have 2 different ordered pairs when I do that. Let's go ahead and do those. I'm going to plug the 4 in and see what I get. So f of 4 would get me 4 cubed minus 5 times 16 when I square it, minus 32 plus 2. All right, I got a negative 46. What I have then is an ordered pair 4, negative 46 that I know is going to end up being a min or a max. It's going to be one of those peaks or valleys. Then I would do the same thing with my negative 2/3. Type that in your calculator, go through all the algebra to figure out what that is. I end up getting a 4.82 is what I round that off to. And that's another point that I know is going to be the min or the max. Now, how do you know if it's a min or a max? That goes back to what we know about this function right here. This is a cubic function. We should know what that looks like. In general, cubic functions do this right here, kind of thing. If you use these ordered pairs, and I know, as a regular cubic, because this was a positive value right here, so this is a regular cubic, as I read it left to right, the first critical point I get there is a maximum, the next one would be a minimum. So if I look at my x values, the first x value, or the smallest x value, the one on the left, would be my maximum, and my next x value, the one on the right, or my larger x value, would be my minimum. So we have to label that right here. This one would end up being my maximum, and this one would be my minimum. We never had to graph that function to know what was going on. And in fact, with that information, I could probably give myself a pretty decent little sketch of that graph. And mine's obviously not drawn to scale, but there you have it. The other type of critical point that we have is a point that we call the point of inflection. It is the point where the function switches concavity. The function, the curve. Now, we don't talk a lot about concavity, but it's kind of whether it's kind of concave up or concave down. And if you look at it, if you look at our tangent line on this one, you can kind of see that the tangent line sits here and is riding on the top of the curve. It's above the curve, and up here you're at the peak, so you can definitely see right here you're above the curve, and you're still above the curve, but there's a spot in here where it switches to being above the curve, and now I'm underneath the curve. You see how that works? That place in there, and it's hard to see on a graph, somewhere in this range right here, it switches from being above to being below. And that right in there is your point of inflection. We can use the derivative to find that point as well. The point of inflection is found by calculating the second derivative, or what we call the derivative of the derivative, which is notated with two little marks. So let's go find our derivative. 3x squared minus 10x. Okay, this is an example that is on your worksheet there. Actually, I take that back. This might just be one that I came up with. You don't have this on your, so just jot it down. That's your derivative. And we can use that to find your min and max. But if I'm looking for the point of inflection, I will find the derivative of that. So that'll become 6x minus 10. And we do the same thing as when we do our min and max, where we set it equal to 0. If you set your second derivative equal to 0, it's going to get you the x value of where that point of inflection is. On this one, when I set it equal to 0, x will be 5/3. Now that's an ordered pair, remember, and I'm going to take 5/3 and I'm going to plug it back into the original function and see what I get back for a y value. All right, so pause that to save us some time there. When I plugged that back in, I got a negative 20 point, I'm going to go with a 0.59. That is the ordered pair on that original graph that I had, where it'll switch, the graph switches concavity, and that's the point of inflection. Let's recap all of this. This is on the back side of that critical point worksheet there. I have this little summary. It is ugly and sloppy, and someday when I get an extra 20 minutes, I'll retype that, but you know, that 20 minutes disappears. So here it is, ugly as can be. There's 3 types of critical points. Do you know what they are? You've got maximums, you've got minimums, and you have points of inflection. And your derivative can help you find all of these critical points. And then this is just a summary of what you do. If I'm looking for the max or min, I'm going to find the derivative. I'm going to set that derivative equal to 0. Solve it for x. On our example, I had to factor to solve it. I ended up with 2. You might have only 1. You might have several. It just varies on your function. To find the y coordinate of those min and max critical points, you're going to replace that x back into the original function to find the y. If you're looking for points of inflection, you're not just going to find the derivative, you're going to find the second derivative. And you set that second derivative equal to 0. Go solve for x. We only got one of them, but you may have more than one depending on how fancy your function gets. And then you're going to plug that back into the original function to find the y value of that critical point. That's your summary. It's not very difficult, but you have to understand what it is you're looking for. And I wanted that, this is a little bit longer video because I want it to make sense in your head. I have one problem. You only have like 4 of these to do for your homework. So there's not a bunch, but I'm even going to do the first one with you. Number 1 says, determine the critical points for the graph. This is my function. It's a cubic. Let's find the critical points. I'm going to start off. Critical points means everything, so max, min, and point of inflection. Let's find the derivative. Once I find the derivative, I set it equal to 0. I'm going to have 2 values here, which should make sense because I have a cubic, so I'm going to have a max and a min going on. Take these 2 x values, plug them back into the original function. I end up with a point 2, negative 20. And then when I do f of negative 2, negative 2, 44. Now which one's which? What's a max? What's a min? Go back to the original. It's a cubic. It's going to look like this. And it doesn't, that's not accurate at all, but just recognize the point further to the left is going to be your max, and the point further to the right is your min. So let's clarify on this, that this is going to be my maximum, and this is my minimum, which actually makes sense. Look at your y values on that. But you have to be a little bit careful as this function gets to be a higher degree and you have more waves. Sometimes you can have a minimum that ends up being higher than a maximum just depending on where you're at on that function. So I like to look at the x values instead. I've got those two critical points. Now I'm going to go find my point of inflection. I have to find the second derivative, the derivative of the derivative. Looking back at the derivative, the second derivative would end up being 12x. I guess just 12x, all right. Set that equal to 0. X is going to be 0. Plug that back into the original function. Oh, this is getting easier and easier. Plug 0 back in here. I'm just going to get a 12. The point 0, 12 is going to be my point of inflection. The thing that's nice about this, if I go back to this min and max idea, this is probably a little bit faster than going to our calculator and finding the min and max, because if you look at the numbers you're dealing with, this wouldn't have fit on a nice 10 by 10 window. I would have had to play with that for a while to find those, and then I have to do the second calc, go do min, max. Sometimes algebra is a lot faster than looking at the graph, even though we kind of like to use our calculator for that stuff. All right, so your homework is to finish up 42 through 44 on that shortcut worksheet. That was where the video started. And then finish this critical points worksheet. You got 3 more examples to do on that. You have a review worksheet. We're going to have our test tomorrow. Good luck.